Okay, good evening. This is Professor David J. De Los Reyes. Okay, it's November 12, 2023, and the time is around 11:11 p.m. Okay, my topic for tonight will be a very interesting one because this will now be the so-called study of the so-called corrected voltage of an alternator. The last time around, I discussed I derived the formula on how to compute the generated voltage of any alternator. And for tonight, we will be discussing the so-called corrected voltage of an alternator. There is a so-called correction because there are some factors which must be multiplied for the theoretical generated voltage, because in reality, there are factors which affect the value of the so-called generated voltage. Okay, let's proceed. The title of the topic for tonight will be Easy Machines, lesson number 57. We are running smooth. We are done with transformers, so we are now on the so-called study of alternator, and we are now on the topic corrected voltage of alternator. There is a correction. The computed generated voltage is just the theoretical value, but there are some factors which affect the value of the generated voltage. Like ourselves, we could not give ourselves a 100% efficiency. So for machines, it's also like that. Okay, let's try to bring out the formula of the so-called corrected voltage for alternator. This is now a general formula, and this is being used under the so-called study of machine design of alternators. And the formula for the corrected voltage, I will try to read the formula. Capital letter E prime, this should be equal to 4.44, the product of frequency, flux, the rate of rotation times 10 to the minus 8. Actually, we derived this one the last time around, and the unit of this is actually volts. But for the corrected voltage E prime, capital letter E prime, this is to be multiplied by a value small letter d. And small letter d, where's small letter d? Small letter d is actually, where's my pen? Small letter d is the so-called correction factor. Okay. Due to this correction factor, the corrected voltage is actually less than the generated voltage theoretically. Because if we try to multiply all the products of this, that is meaning the frequency, the flux per pole, and the RPM of the generator we are talking about, okay, it is to be multiplied by value D, and this is termed to as the corrected voltage. Okay. This value here, D, actually is a very complicated thing because it contains two components also. And these two components are actually the product of capital letter K with the subscript P times capital letter K with the subscript D. Meaning small letter d, the correction factor is the product of capital letter K with the subscript P times the capital letter K with the subscript D. And the meaning of K sub P, it is the so-called pitch factor. Later on, I will try to discuss what is pitch factor. So, but for now, we will just concentrate on the formula. K sub D, it is the so-called distribution factor. And E prime is the corrected voltage. So these are the needed formulas under the corrected voltage of alternator. This is the formula for the corrected voltage. And this is the formula for the so-called correction factor. Okay, these are formulas, so it seems we are now on the so-called study of machine design. Because This formulas here involves the physical, what they call this, property of the alternator that we are talking with. It involves the physical characteristic, meaning the total number of slots, maybe how many poles is the given alternator, something like that. Because those parameters are actually needed here in the computation of the generated voltage in the so-called distribution. Okay, let's try to bring out another two formula, okay, which are needed in the so-called value of letter D. Because I gave you the value of K sub P and K sub D, but there should be a formula on how to compute K sub P and K sub D. For the pitch factor, capital letter K with the subscript P, this is now trigonometry. That's why before we go to higher up engineering courses, we pass by trigonometry. So this is now a part of trigonometry. Capital letter K with the subscript P is actually the sign of the quantity P degree all over 2 closed quantity. Later on, I will try to discuss what is P degree. And the distribution factor, capital letter K with the subscript D, is actually, it's more complicated one. So, I put what they call this square on it. So when you try to watch my video, you will see it clearly, you know. K sub D will be sign of the quantity. This is now, it combines algebra and trigonometry already. So, because there are some open and closed quantities in, that's a part of algebra. Sign of the quantity n, small letter n, times D degree all over 2, closed quantity, all over n, sign of the quantity D degree over 2, closed quantity. Okay. We'll try to discuss what is P degree and what is D degree and what is N. Okay. Because we will be getting these values here or parameters from the physical characteristic of the alternator. Okay. So it seems we are now on the so-called study of machine design. Okay. Where capital letter P with the symbol degree is the number of electrical degrees between coil sides. Between coil sides. To imagine this one, it is like this. One coil is this one. Just one coil. Okay, it enters slot number 1. It goes to the other, to the back. Okay, then it enters slot number 5 at the back. Then it come out on slot number 5 in front. So meaning, this part here enters here. Okay, it goes to the back. Then it enters slot number 5. Enters here. Okay, so this one here is actually this. It goes out at slot number 5. The angle between slot number 1 and number 5 is termed to as the so-called P degree. Okay? That's why I draw the, what they call this, spread out drawing of the stator of an alternator. It was spread out, right? So this is the teeth, this is the slot, teeth, slot, or tooth. Tooth, slot, tooth, slot, tooth, slot. These circular things here are the conductor as seen, you know, frontally. These are conductors. Okay? And if you try to, what you call this, imagine that conductor inserted in the slots, it is something like this. This is slot number 1. It goes to the back. Then it enters slot number 5. The conductor enters here. It goes back. There's a connection at the back. Then it will enter slot number 5. It is this. That's one coil. So this is the winding. Okay. So if this is slot number 1 and number 5 comprises of maybe 50 turns, this is 50 turns. Okay. It enters here, it goes out here, then it go back to slot number 1 again, then it will enter slot number 5. It depends on the design of the alternator. How many turns per coil, okay? but I am only showing you one coil or one winding. So P degree, it is this. Okay? It is the number of electrical degrees between coil sides. This is the entrance of the first coil. This is the other end of the continuation of that coil, and the number of electrical degrees in between them is actually the so-called P degree. Okay? And what is D degree? D degree is the number of electrical degrees between adjacent slots. Okay? So we are talking the number of electrical degrees between slots. This D degree here, it is this. Okay? Considering slot number 2 and number 3, this is the conductor, right? This is the conductor. The number of electrical degrees between slots is actually termed to as D degree. Small letter d, symbol degree. Okay? So we now know degree, D degree. The one we use in these formulas. Okay? At least when we are using these formulas, try to imagine these values here from the physical appearance of the alternator. That's why I have drawn this physical appearance of the alternator frontally, you know. What is N? Small letter n. Because we needed the value of N here. N is actually, I place it here, the number of slots per pole per phase. Slots per pole per phase. N is actually equal to the number of slots, okay, divided by the number of pole, the number by the number of phases. So it will just be simply phase. So if the number of poles is actually, supposing it's 4, and the number of slots is equal to 24, right? An example. And the number of phase is equal to, we are talking 3 phase now here, because alternators or generators for power generator is always a 3 phase. So the number of phase will be 3. So the total number of slots, this is just an example, guys. So if the total number of slots is 24 and the number of poles is 4, right? And the number of phase, of course it's 3 phase, it's 3. The value of N will be 24. We divide that by 3 or by 4. Okay? Then we divide that again by 3. Okay? What will come out? So it will be 24 over 12. And 24 over 12 is actually a 2 degree. So the value N here should be computed something like this. You divide the number of slots by the number of poles and divide that again by the number of phases. Okay? And you will get how many degrees between slots. The number of electrical degrees between slots, that's the degree. Right? Okay, that's it. Oh, I got a little note on the so-called, because the next time around, I will be discussing some annotations regarding this pitch factor and distribution factor. There are some observations here. We'll talk it verbally, you know, right? It's theoretical explanation. So it's a storytelling regarding this pitch factor and distribution factor. Okay, for pole pitch winding, the value of K sub P is actually equal to 1, and the value of P degree is exactly 180 degrees. And for fractional pitch winding, the value of pitch factor is actually less than 1. It's less than 1. So if this is less than 1, okay, of course, the corrected voltage is actually less than the theoretical voltage given by this formula here. Okay? The usual one we are using in the so-called design of alternators is actually, I think they always use fractional pitch winding, in which the value of P degree is not 180 degrees. It's less than, if P degree is less than 180 degrees, it is termed to as fractional pitch winding. Why is that so? It is something like this. What's the formula for K sub P? K sub P is equal to sine of P degree. If P degree is 180, exactly 180, divided by 2, 180 divided by 2 is actually 90 degrees, right? And if we try to take the sine of 90 degrees, this is now trigonometry. Sine of 90 degrees is equal to 1. K sub P is equal to 1 if P degree is 180 degrees. Right? That's why I place it here for pole pitch winding. If it exactly the distance between a north pole and a south pole is 180 degrees, that is termed to as pole pitch winding. Right? But if the value of P is less than 180 degrees, supposing P degree is only measures from slot number 1 to slot number 5, so it will be 5/6 times 180 degrees. So this will become 30, right? And 5 by 30 will be 30. It's 150 degrees. So an example of a fractional pitch winding is P degree here is 150. Meaning the number of slots involved, is not a complete thing from a north pole to a south pole, because from a north pole to a south pole, for this figure, it is 6, right? 1, 2, 3, 4, 5, 6, right? So if the location of where the winding will enter and the winding will come out is not exactly between north pole and south pole, we term to that one as a fractional pitch winding, and supposed to be the value of K sub P is less than 1. Why is that so? It is something like this. If P degree is equal to 5/6 times 180, or this should be 30, it's equal to 150 degrees. K sub P should be equal to, we use this formula, sine of P degree. What's P degree? 150/2. And this is actually 75 degrees. And the value of sine of 75 degrees. If an angle is less than 90 degrees, the value of the sine is actually less than 1, because sine of 90 degrees is 1. So if we try to take the value of sine of 75, take the sine value, it's 0.9659. It is equal to 0.9659. So imagine this value here. We will multiply that to the theoretical value given by this formula here. Of course, the corrected voltage will be less than this theoretical value here. It's not 100%, because it's not always that the entrance in the outlet of the winding that is wound on the slots is exactly 180 degrees. And I think in the actual design of alternators, it is always less than 180 degrees. Because the distance between this slot number 1 and number 6 is too far, right? Actually, there are windings in which it will enter slot number 1 and it will come out at slot number 3. So it's a shorter distance. But that's actually the one they are doing in the actual design of alternator. So this pole pitch winding, they don't usually use this one. They always use the so-called fractional pitch winding, in which the distance of the entrance of the winding put in the slots is actually very near the one that it will come out. For a pole pitch winding, this might enter at slot number 1 and it will come out at slot number 3. Right? And this is termed to as fractional pitch winding. fractional. Okay, that's it, guys. The next time around, I will be discussing some annotations regarding pitch factor and distribution factor. But for tonight, I have given you already the formulas on how to compute for the corrected voltage, okay? And the corrected voltage is the product of the pitch factor and distribution factor. And the formula on how to compute for the pitch factor will be sine of p degree over 2 closed quantity. And the value of the formula on how to compute for the value of the distribution factor, it's a little bit more complicated than the first one. Sine of n times d degree all over 2 closed quantity all over n sine of quantity d degree over 2 closed quantity. And where this value p degree emanates, it came from here. And for this d degree here, it also emanates from the physical characteristic of the alternator. And for the value of n, it's a theoretical value because the formula on how to compute for the value of n is actually the slots. You divide the slots, you divide that by the number of poles, then divide that again by the number of phases. So we could actually compute for n. Also, this n here emanates from the physical characteristic of the alternator. Total number of slots, total number of poles, and the total number of phases. Okay, that's it for tonight. This is Professor David J. De Los Reyes. Good evening from Los Angeles.